Hey, this is Ash. I'm going to be talking about Benthos, which is a dull, resilient, and quick to deploy stream processor. If that doesn't tell you enough, well, you're in luck because I'm about to explain exactly what it is and what it's useful for. And I've also got some interesting examples of how Meltwater currently uses this in prod to treat you with if you make it to the end. So the first thing I'm going to answer is, well, why? Why does this project exist? The problem I'm trying to solve here is that streaming pipelines tend to be quite volatile. So they constantly change. That could be things like the queue systems and protocols between components, but also the format of payloads as they travel through a pipeline. And that could be for all kinds of different reasons. It could be because we're using new technologies, implementing new features, but also integrating with new data sets, working with new teams, for example. And every time stuff like that changes, as an owner of a component in a streaming pipeline, you have to go back and do these stupid repetitive development tasks. So I won't bore you by going through the list one by one, but everything here I've had to do personally multiple times in multiple code bases. I'm sure there's lots of you out there who've had to do the same, and it's all junk. This is all trash, isn't it? Nothing here is fun. Nothing here is going to be the intellectual property of a company. Some of you are probably watching this thinking, "Oh, but I like doing some of these things." Well, okay, I am also scum, and I also enjoy doing some of these things. But the point is, there are real people out there. And it's important to remember that they don't want to do this stuff over and over again. And that could just be because they're overwhelmed. Like maybe you've got a huge platform, lots of components, and in order to use a new queue system or integrate with a new data set with new formats, it's just going to be too much work, or you're constantly struggling to keep on top of it. Or potentially, you just get fed up. So maybe you're a data scientist, you work on NLP, services, for example, and you just want to focus on that. You don't want to have to worry about all this dumb, trivial stream junk. Why? It's such boring tripe. I want to just focus on my thing, which I'm good at and gives value to the company. So what I wanted to do was try and make a single isolated component that those people could just drop into a pipeline at any point that it's necessary, and it will just do all the boring stream stuff. And they don't have to worry about it. And it's not going to lock them into a specific queue system. It's not going to lock them into a specific technology. It's not going to lock them into a specific language because their components can be completely isolated. They just fit in the pipeline however you want to. And the idea is then eventually if you don't need something like this, you can just take it out because you're not locked into it in any way. It's integrating with the same queue systems you use. You don't have to worry about it. Now, obviously, the main requirement here is that it's got to connect to all the same queues and stream protocols we use right now, anything we might use in the future. It's got to be able to do all those same common data operations I just listed. And the candidates here are anything that's common in stream pipelines, trivial to describe. So it doesn't necessarily need to be trivial to implement, but trivial to express the behavior, and volatile, so stuff that changes quite often. And a big deal for me was this thing needs to be ready to deploy. So you don't have to compile it or build it yourself. There's minimal friction between you as a team deciding you want to deploy something like this and actually being able to do that. And that means Docker images, tar zip archives, RPMs, stuff like that. And obviously with that comes the need for it to be config driven. All the behavior needs to be in that binary ready to go. And so you expressed it through config. And it needs to be well documented, obviously. That was a big focus of mine from day one, was making sure that you could use this thing in isolation. And for us, it needed to be very resilient, so it's got very resilient defaults. I'll explain that in another slide. And it's got to be low performance overhead. So we've got performance critical pipelines, and obviously if we're dropping this thing in multiple places, it needs to therefore have a negligible impact on throughput and latency. Right, let's go through some of the features. The main feature of Benthos is obviously it's got a range of sources and sinks. Anything on this list is something you can both read from and write to, except for Elasticsearch, which you can only write to. If you've got a use case for arbitrarily reading Elasticsearch, I'd like to hear it, and I'll consider putting it in, or I won't. And any of these you can combine, so you can have multiple inputs, you can have multiple outputs, and the way that outputs work is you can pick a brokering pattern, so you could pick fan out or round robin, etc. Now it's got support for a buffer, so by default Benthos doesn't have a buffer, and that's a big deal for resiliency because it means the input is directly coupled with the output, and I'll explain that in a minute. And I think most people don't want a buffer, just don't do it. But if you do need a buffer, for example, for things like downstream back pressure or leveling out input spikes, then you can either choose a memory-based or a disk-backed buffer based on your config. And that might be useful for doing things like consuming Firehoses. And I've got an example of that in some of the future slides. But for most people, you don't need a buffer. Stop it. Stop putting buffers everywhere, okay? Please. And Benthos has this concept of processes. So processes are essentially a function, and they will consume a message and then spit something else out. And they can do all these trivial things. And you can list as many of these as you want in your config, and they'll be executed in the order that you write them. So the kind of things they can do is they'll do batching, so they can combine messages to create bigger batches. They can also break batches down. They can do transformations, so you can use metadata to set the content of a message, and also the other way around, you can use the content to change metadata. You can do compression and archiving in either direction. You can do arbitrary JSON mutation to a payload, and that's with James path queries, which is very similar to JQ syntax. It's very powerful. You can do grok. There's also content-based filtering. So filtering can be done with James path queries that return booleans, or you can do text and regular expression-based comparison operators, and they can be combined with boolean logic, things like that. And this can also be used for multiplexing to different outputs, and I've got an example of that as well in one of the future slides. And it can do stuff like deduplication. So that can either be with a local cache or with a distributed cache, so it can be shared across Benthoses or Benthi or Benthon. And it all comes together in these 4 config sections. So you've got an input section, you've got a buffer section, you've got a pipeline section, and this is where you would specify your processes. You can also lock it to a specific number of processing threads, and you've got an output section. Now don't dwell on that for now because I'll explain that in more detail. And it's got resiliency without persistence. So this is where I'm talking about inputs being coupled with outputs. So if you don't have a buffer, Benthos has been architected such that if it's reading from an at least once protocol with acknowledgements, and it's writing to an at least once protocol with acknowledgements, it doesn't acknowledge receipt of a message it's read from the source until that message has made its way all the way to a sink and the sink has confirmed receipt of a message. And what that means is you get the guaranteed resiliency of the protocols you're using, and Benthos is therefore not the weakest link. It's completely crash resilient. You can kill it at any point. It can be hit with a comet. It doesn't matter what happens to a message while it's in transit within Benthos, because it doesn't get acknowledged until it's already left the service, which means it's super safe to just stick in between any at least once protocols. Obviously, if you introduce a buffer, for whatever reason, but don't do that, then your resiliency is going to depend on the buffer that you choose. Now, the way that this looks internally is you've got like an input layer and you've got an output layer, and then you've got any number of things in the middle depending on your config. And each input will work asynchronously. It'll be reading messages, but it won't acknowledge them. And then what it does is it sends a transaction through this transaction bus. And a transaction is the payload, and then also a mechanism by which any component in the pipeline can send a response back containing the acknowledgement to that specific input. And it will not acknowledge receipt of a message until it receives that response. Now, that could mean that the message gets sent and some sort of filter gets it and then removes the message based on the filter, and then it could send a response back saying, yep, the message has been dealt with. Or it could make its way all the way through the pipeline, get to an output, and then the output would try to send that message on its respective protocol. And then depending on what kind of response it gets back, it will send that to the input. And what happens if an error occurs will depend on the input itself. So for example, with Kafka, it just won't commit the offset, and it'll just keep retrying the message every now and then. And obviously, if it never makes its way through, it just won't be acknowledged. If, for example, you use RabbitMQ, then you've got an option here of maybe the message gets sent back to the broker, and you just say, look, I can deal with this, maybe give it to another service. But usually this is down to the input itself and your config. And also this works with batches. So even if you're reading single messages from, say, RabbitMQ, and you're combining those into, say, a batch of 100 messages, they will not be acknowledged. And what happens is that entire batch will get sent through the pipeline, and they'll all get sent off to some destination. And then finally, they all get acknowledged at the same time. So even if you're batching, you still get full guaranteed resilience. And this thing's easy to deploy. So it's written in Go, which means you get a nice static binary with 0 runtime dependencies. The config is either in YAML or JSON format, and you can pick specific fields to set with environment variables if you want to. That's useful for things like Docker deployments. You've got a choice of metrics destinations, so there's statsd, and there's also Prometheus. And also, if you can't be bothered to set up an aggregator, but you want to debug a pipeline by using metrics, you can set an HTTP endpoint where you can hit it to get a nice structured JSON object of metrics for the lazy people out there. There's a Docker image, and the way that the Docker image works is by default it comes with a config file where every possible field in the config can be set with environment variables. And what that means is you can just pull the Docker image right now, and you can set the input fields, a buffer potentially, buffer fields. You can have a processor, set any processor fields. So for example, you could have a James path query in there, and then finally you can set the output and the output fields all with environment variables. There's no need to copy a config into the container, but obviously you can do that if you want to. And it's got tons of documentation up the wazoo. So obviously this was a concern of mine from the beginning because I'm a solo developer on this project and I wanted to make sure the documentation was always up to date. So what I do is I generate config examples, which is a full workable config example for every input, buffer, processor and output type in Benthos, and they're always checked into the repo. But you can also generate these from the binary. So if you grab the binary and do this command print YAML and then -- example, you can give it a comma separated list of types that you would like to include in your example config, and then you can just pipe it to somewhere. So for example, this command would make a Kafka input, a JSON processor, and an AMQP output, and it would just make it for you. And then all you have to do is set the particular fields that you want, and it's good to go. You can also print documentation from the binary, so that you can create a nice markdown file where it's the same one that's in the repo, and it will just give you descriptions for every single input type and a little config example, and that'll tell you any caveats or explain what a particular input is if it's not particularly obvious. And obviously this is all in the repo, which I would usually recommend people just go to the repo and find it in there. And everything I've described so far has been one continuous stream of data. So even if you have multiple inputs and multiple outputs, it's one flow. Now, for the most part, I think that's what people usually want. But you can run Benthos in streams mode, and that allows you to have multiple isolated streams all in the same process. Sorry. And this is pretty cool because you can either point it to a static directory of config files and it will just walk the directory tree and find all the configs you put in there. Each one will become a stream, or, well, you can use a REST API. So this allows you to create new streams, update streams, as in update the config, patch a stream, so patch the particular fields you want to change if it's a big config, get the status of a stream, including its current config, and delete streams all while it's running. So this is a runtime dynamic. You can just do all this on the fly. And that means you can set up services and tooling that will just create streams as and when you need them and destroys them at a certain point, which is really cool, basically. And that's most of the features. Obviously, this stuff's always changing, so this is always going to be a subset of what Benthos actually does. But now I'm going to go over some of the actual configs and things that you can do in detail. So this is the config I showed earlier where you've got an AMQP input, and that could be RabbitMQ, for example. And then you've got a buffer section, and this is a memory buffer of 50 meg. Then you've got a pipeline section, and in this case we've got a decompression processor, which is gzip by default, and then we follow it up with a James path query. So what this would do is it would decompress gzip payloads that we're getting from RabbitMQ, and then afterwards we would apply this James path query to change the JSON contents of the decompressed message, and then finally that would get sent to Kafka from our output section. Now we've said here 3 processing threads, so maybe that means we've got 3 CPUs or whatever, who cares. This is what it looks like under the hood. So we've got these 4 sections. And depending on your config, some of these sections may or may not exist. So for example, if you didn't have a buffer, this section would not exist completely. It would just directly link the input with the pipeline layers. And each layer can have any number of asynchronous components within it. We've only got one input consumer at this point, and that's being written into a memory buffer. And then the memory buffer is being split across these 3 processing pipelines, and then they all go to this one output producer. Now, whoever wrote this config, they're a bit dumb, I'm afraid. And I wouldn't recommend working with this person in the future. They've really dropped the ball here. I mean, yeah, they've really made a pig zero this one, because what they've got here is they've got an at least once protocol potentially. So RabbitMQ supports acknowledgements, and they've got an output which will also give you an acknowledgement, which is Kafka. But they've decoupled the two. They've put this memory buffer in the middle, which means if there's a crash or if the server dies or something like that, all the messages in this buffer are lost forever. And even if it were a disk buffer, you could still get disk corruption. Somebody could just steal the disk if they got into your data center and run away with it. So this is a trash config, and whoever wrote it is trash. What we'd want instead is something like this, where we take out the buffer completely, and we have multiple input consumers, and then they're directly linked to the output. So what will happen in this case is messages will never be acknowledged until they've reached Kafka, essentially. Now the reason why we have to have multiple inputs here is because if we only had one, because it's coupled with the output, and it'll wait for an acknowledgement before it sends another message through, so it's only ever going to be using one processing thread. And if we have at least the same number of consumers as we have processing threads, that means we can potentially saturate these. I put in 6 here because why not? Why not just keep adding them? You could obviously tune this if it's still the bottleneck. And these would all be consumers consuming from the same key, essentially from RabbitMQ. The messages would just automatically get distributed across them. And what this looks like in config is something like this, where we've got we've now got an input broker, and that's an input type which has a child inputs where you can just list an arbitrary list of different input configs. Because we just want the same input config 6 times, we can actually take a shortcut here, write it once, and then we say copies 6. And what will happen is anything that's inside this inputs array will be made that many times. So we end up with 6 AMQP consumers that all match. We've removed our buffer, so we say buffer type none. We could just delete that section entirely because it's none by default. And then the pipeline and output sections stay the same. Now, if it turned out that the output was the bottleneck here, then obviously we wouldn't be saturating our CPU threads. So what we could do in this case is we could do 2 things. We can either batch the messages up, which I would recommend first because we're writing to Kafka. So we could do that with processors. We'd have a processor, say here or here, which just batches and maybe makes a batch size of, say, 100 messages. Or the other thing that we can do is we can add more output producers. So they would be working asynchronously, and a message from the pipeline section would just automatically get allocated to whichever one's available. And that would be kind of like an ideal situation here. And that's how you get the most out of Benthos. Because what you can do is you can lock the number of processing threads to match a resource, which would usually be CPU if it's CPU heavy processors, but it could be some other resource. You've got a number of input consumers, which you can tune depending on whether or not that's the bottleneck. As long as it matches the number of pipeline threads at least, then you'll saturate them potentially. And then you can tune the number of output producers if that turns out to be the bottleneck. And obviously you could also play with batches to try and improve the throughput that way. And what this looks like in config is the input section is the same, buffer section is the same, pipeline section is the same, but now we've got this output broker type, and that is basically the exact same config as the input broker, except we have a new field which is called pattern, and that specifies the brokering pattern we want to use. So this is where you could specify fan out, round robin. In this case we say greedy, and greedy means we don't care about distributing the messages evenly across the outputs. We just want messages to get routed to whichever output is ready to go. So it's basically the highest throughput brokering pattern for Benthos. And that's it. Because they're all going to the same destination, we'll pick greedy because we don't need to balance the messages. Now this is a different type of config. This would show content-based multiplexing. So what we're doing is we're reading messages from standard in, and the message could potentially be an error type or it could be a normal message. And what we want to do is we want to read all the messages to this HTTP output except for errors which will route to standard out. Now we can do that with content-based multiplexing, and we do it with filter processors. Now every processor I've shown you so far has been in the pipeline section, and that's usually what we want because we want our processors to apply to every message coming through the pipeline. However, you can put processors on a particular input or a particular output, and that allows you to have different behaviors depending on which protocol is being used, where it's coming from, etc. And in this case, what we want to do is we want to set our broker to be fan out, which means every message gets routed to each of our outputs. And then what we do is we list our outputs and we put a filter to determine which messages get routed to it. So here what we do is we have a filter for standard out that is of a type James path, which means we're doing a James path query here, which is going to return a Boolean to determine whether the message goes through or not. And the query is whether or not body.type is equal to error. And obviously if it is, it will get routed to standard out. If it's not, it'll get dropped before it reaches the output. Now on the HTTP server output, we do the exact opposite. So we've still got a filter, type James path, and now we're looking at body.type does not equal error. And what that means is now messages coming through will either go to the standard out or they'll go to the HTTP server. And that's it. That's how you do content-based multiplexing. Obviously these queries could be huge. They could be combined in different Boolean expressions, but that one's quite simple. So that's a few demonstrations. Now I'm going to show you actual real examples of how we're using this at Meltwater. Now we're using it all over the place, but usually it's being used for very boring stuff. So I've tried to pick out some examples where we're doing something maybe common to other teams, but is also not massively boring. So this is an example where we had a bunch of components in a pipeline that we're reading from Kafka, and then we wanted to reuse those components to consume data from an S3 bucket. So this was integration with another team, and the way that they would deliver the data is it gets stuck in our bucket. We wanted to consume it using the standard Amazon S3 and SQS pattern where we're listening for events on SQS, and then that prompts us to download something from S3. And the format of the data they would put in the S3 bucket is it's a tar gzip archive of enveloped JSON messages, and the contents we actually wanted is this envelope stringified JSON field, which becomes a new JSON object. And that's when we wanted to write into Kafka in order to make it look the same as the data that we were used to reading from that Kafka queue. And the config for that is pretty simple. So what we had to do is read from S3. So we use the standard S3 input type. There's some fields in here for specifying an SQS URL. If you leave these blank, then what it does is it will just download everything in the S3 bucket and then it stops. But what we wanted to do is read from an SQS queue, and then that would give us events to download from S3. So you put down the URL and some other fields. We didn't need a buffer in this case, and our pipeline. So what we're doing here is we're doing a decompression, which is type gzip. So we decompress the tar.gzip archive, then we unarchive the tar.gzip archive, and what that results in is a batch of JSON messages. And then what we needed to do was de-envelope the JSON payload that we actually wanted, which was a stringified field, and that field could be found at payload. So we do this JSON processor, which has a bunch of arbitrary operators, and one of them is select, where what it does is it will select the contents of a field, and the contents will become the new payload. So we effectively de-envelope here. And then finally, we just send that out to Kafka. So nice and simple. And then we didn't have to change any of our existing components, and we could carry on using the pipeline exactly as it already was. So we were actually combining the streams here rather than having to have separate components, separate deployments, all that mess. Another example we've got is the Twitter Firehose. So we wanted to consume the full Twitter Firehose with only Benthoses and a distributed memcached. Now, the way that we consume the Firehose is we essentially get a partitioned Firehose, which means we can consume multiple times, and each consumer gets a subset of the Firehose. And we also get redundancy, so each of those partitions can be consumed twice. So what we wanted to do is have a cluster of consumers in one data center and then a cluster of consumers in another data center. And the reason why we want the redundancy in this case is because if you don't consume the Firehose quick enough, say you get a spike or something like that, or you could just get randomly disconnected, but you'll get cut off. And every time you get cut off, you potentially get message loss. Now, there is a Benthos we could trigger to do a backfill, but we didn't want to have to trigger that every time we get some random disconnect or something. So what we do instead is we have redundancy, and that gives us a little bit of wiggle room, a little bit of flexibility. So if one consumer dies, there's usually another one that is continuously streaming the same data. Now, obviously, we didn't want to write the entire Firehose twice into our Kafka cluster. So what we did is we set up a distributed memcached, which all the Benthoses share, and they then deduplicated their tweets by the ID string, the JSON object. And this is what it looks like internally. So we're consuming from the Twitter Firehose. That then gets written into a buffer. Now, this is a good example of where you might actually want a buffer because obviously if you don't consume the Firehose quick enough, you get cut off. But we didn't want to have to deal with the worst case scenario in terms of capacity because it's expensive. And most of the time you just get these weird spikes in the Firehose that it's not the same consistently. So what we do instead is we stick a buffer in there. And every time we get one of these spikes, we can just level it out over time. And then that gets distributed across these processing pipelines. Now, the processing pipelines, for the most part, will just be sitting on a memcache request. So what ends up happening is we tune the number of pipeline processing threads to match the maximum number of parallel memcache requests we want to make in order to not stress it out. And then finally, all of that gets sent out to Kafka. And this is what the config looks like. So the input type is the HTTP client input type, and that's not Twitter specific. And what we do is we say stream enabled because otherwise the payload would be expected to be a single message, but in this case it's a continuous stream of line delimited messages. So what we do is we say stream enabled, and then we dump that into a memory buffer of 500 meg, and then we've got these 16 processing threads, and the processing threads do two things. So the first thing they do is a James path filter, and what the filter is doing is it's checking that it's a valid JSON message, so we didn't just get some junk or a keep alive message. And then secondly, it removes error types. So the Twitter Firehose occasionally gives you these error objects, which describes the condition of the connection you've got. We want to obviously remove those before writing them into Kafka, and we can expose them in another way anyway. So we take those out the Firehose completely. And then after that, we send it into this dedupe processor. Now the dedupe processor takes a cache type, and that's configured elsewhere so that the cache type can be shared across different processors. And it's like 4 lines or something, but I couldn't fit it here. It's just to say memcached cache, this is the address, this is the TTL. But anyway, so you point out the cache here, and then it's got a key field, and the key is what you're using to deduplicate on. And the way that this works is it uses function interpolation. So you can have a string here that includes these functions, and the functions can be used to extract metadata and also the contents of the message through JSON fields, for example. So what we do here is we prefix it with tweet dash, and then we get the ID string of the message coming through. We could optionally leave the key empty, and what that would do is it would deduplicate based on the entire contents of the message, and you could hash it. But in this case, we didn't want to hash. We just wanted the ID string. And then finally, everything gets sent out to Kafka. And that was it. So this is running on prod right now. It's been running for months and just works. We're happy with it. We're satisfied customers. And that's it. That's all I wanted to show. So hopefully you found that interesting. Feel free to grab a copy of it and play with it. I'm actually going to leave that decision up to you. I'm not going to force you either way. Thanks for watching.